introduce the IFISC PhD student, Miguel A, who will present his thesis entitled Electrically and Thermally Driven Transport in Interacting Quantum Dot Structures, completed under the guidance of Professor Nchez. And we'll also like to introduce the committee members who form the panel. And I'm the chair. My name is Antti-Pekka Jauho from DTU, Denmark. On my right, I have Professor Gloria Platero from IFISC, Matrid. And on my left, Professor Leonid Glazman from the University of Yale. And at this moment, I will just hand the floor over to Miguel, who will give us 1 hour talk about his work. Miguel, please.
Yeah. Welcome, everyone. Right now, I'm going to present my thesis called Electrically and Thermally Driven Transport in Interacting Quantum Dot Structures. This work was supervised by Professor David Sanchez. Here I present the context of this talk. I will introduce the main aspects of this thesis, and then I will talk about the most relevant works of the thesis, going from single dot to double dot structures. Then at the end, I will give some conclusions and will explain some future work. I want to stress that this does not include all works of the thesis, and for check the other works, you can look to the manuscript. Okay, let's start. First, I will introduce what a quantum dot is. A quantum dot is a region in space where electrons are confined in all dimensions of space. These, for semiconductors, quantum dots are created in the interface between two semiconductors, yielding a two-dimensional electron gas. Then, by applying some gates at the top of the semiconductors, one creates electric barriers where electrons cannot cross, in such a way that in a small region one can create a quantum dot inside. These devices, these quantum dots, have the advantage that they are easy to manipulate. For example, with another gate, applying a voltage to another gate, one can modify its internal density of states. Additionally, these quantum dots can have the size of nanometer scales. So electron-electron interactions inside these systems are important and should not be negligible. Additionally, these systems can be modeled with a simple model with the electrostatic model, where it replaces its part of the quantum dot as a circuit component. So I have said that interactions are important. This yields to one phenomenon called Coulomb blockade, and let me explain this. For example, we have a quantum dot connected to two reservoirs. And in these two reservoirs, one applied voltage bias between these two. If the quantum dot has an energy level, electrons can go from one side to the other, and electric current will flow. Nevertheless, if the quantum dot contains one electron, and another electron has to cross the quantum dot, this will have to overcome the electrostatic energy U, which is the repulsion between electrons. So this phenomenon can be seen in experiments in the electric conductance, where one can find equidistant peaks, on which the distance between these peaks is basically this electron-electron interaction energy. Additionally, if we plot this conductance as a function of the bias and gate voltage, one can find these diamond structures where transport is forbidden inside. These are Coulomb diamonds, and is a signature, and these are signatures of the Coulomb blockade effect. As far as the interactions become more important, one goes to the phenomenon of the Coulomb effect. and this first occur in metals with delocalized electrons in interaction with a magnetic impurity with a given spin. One characteristic of this Coulomb effect is that, for example, for normal metals, as we decrease the temperature, the resistance also decreases. But for a metal with magnetic impurities, what happens is it reaches a minimum and then increases again. This is due to the Coulomb effect and can be modeled with the Coulomb model, which takes a Hamiltonian with two parts. One is the part of the delocalized electrons, and the second part is the antiferromagnetic coupling between the localized electrons and the spin of the magnetic impurity via Pauli matrices. Additionally, this has a coupling strength, which gives the magnitude of this antiferromagnetic coupling. After applying a perturbation expansion of this Hamiltonian, one can obtain a logarithmic scale, a logarithmic term in the resistance. This logarithmic term is the responsible of this resistance minimum. I want to stress that this expression at zero temperature diverges, and this is proves or shows that this phenomenon is a non-perturbative phenomenon which takes many bodies. And one can define a characteristic energy scale that where this resistance minimum occurs, and this perturbation expansion will be valid for temperatures above this energy scale. And this is the Coulomb temperature, which depends on the bandwidth of the metal, the density of states of the metal, and on the amplitude of the coupling strength. For quantum dots, this logarithmic term, instead of being in the resistance, appears in the conductance. This is due to a geometrical phenomenon, and because for a book metal, the electrons has a channel where can go without crossing the impurity. So they can move freely, or they can go to the impurity and go outside. On the other hand, for an artificial impurity, which is the quantum dot, the electron has to cross the impurity, and this means that this is the only channel that the electrons can cross, and then this will favor the electric current. Additionally, the fact that we are in these quantum dots has to be at low temperatures, as we said before, and start Coulomb interactions in such a way that the electric level, the energy level of the quantum dot is only contains one electron. This phenomenon will also, as we favor transport, increase a new channel of transport, which is an energy level, a resonance in the Fermi energy, and this is called the Kondo resonance, or Abrikosov-Zull resonance. So in experiments, one can observe when they plot the conductance as a function of temperature that this logarithmic scale occurs at some point. But at very low temperatures, it reaches the unitary limit, which is proportional to the quantum conductance. Additionally, if we renormalize the temperature, one finds that the conductance follows a universal shape. Additionally, when we plot the conductance as a function of the bias voltage, one can find at b equals 0 a peak. This peak comes from the Kondo resonance and is called zero bias anomaly, and is a signature of is also a signature of the Kondo effect. This, when we plot as a function of bias and gate voltage, one find that this Coulomb diamonds has a line at voltage 0 due to this zero bias anomaly, but only occurs when the electron has when the level has only one electron. So we have an odd-even behavior of the Conde effect. Right now, let me introduce the system and let me talk about thermoelectrics. What we are going to study is a quantum dot system connected, normally connected with two leads. Each lead will have a temperature and electrochemical potential in such a way that one can find a voltage or a thermal bias. As we know, when we apply a voltage in this type of systems, one can find an electric current, and this electric current can, the characteristics of this electric current can be seen with electric conductance. On the other hand, when we have a thermal bias, one obtains a heat current. A heat current will flow along the system, and one can measure the characteristics with the thermal conductance. But this is not the whole story. We have also cross effects. A thermal bias also induces electric current, measuring with the Seebeck coefficient of thermoelectric conductance, and a voltage can also induce a heat current, which can be measured with the electrothermal conductance. This is thermoelectrics, and we will study this type of these parameters along this thesis. So let me start. Right now I'm going to explain one of the works, which is about molecular junctions. In this moment, instead of having a quantum dot, we have a molecule which will be controlled with a gate, and it will be connected also to left and right reservoirs. But let me explain first previous work. This previous work, they measure a ferrocene molecule in contact with gold reservoirs in such a way that one can find current across this molecule. If they when they measure the conductance and they show some kind of diamond structure, and when they plot the conductance as a function of the gate voltage at a given bias voltage, they found two peaks. And when they study with these peaks as a function of the temperature dependence of these peaks at different gate voltage, they observe that in the maximum, this current will decrease with temperature. In the valleys, the current will increase, and in the middle points, the current will stay constant. They try to they fit these results with a non-interactive model using Landauer formalism, and they observe that the results agree with the experiment. Right now, we are going to show that also taking an interactive model can also fit the same experimental curves. So let me explain what is the interactive model, and this will be the Anderson model. This Anderson model takes the Hamiltonian of the leads, which right now we distinguish the lead with alpha. K is the wave number of the electrons, and sigma the spin. Then we take the Hamiltonian of the molecule, which takes the energy level, which depends on using the electrostatic model that I explained before to the gate and voltage bias, and it depends also in the changing energy U, which is the repulsion between electrons in the level of the molecule. Finally, in order to connect these two systems, we define the tunnel Hamiltonian, which allows hopping between the molecule and the reservoirs. Using this Hamiltonian, we use the Green's function formalism in order to find this retarded Green's function, which takes two poles, one centered at the molecular level and the other one centered at the molecular level plus the interaction energy, and weighted by the occupation of the level of the molecule. This occupation number is also dependent on the Green's function. So we are dealing with a self-consistent calculation. And this occupation also depends on the Fermi function. So this Green's function will be also dependent on the electrochemical potential and the lead temperature. Following this, we plot what on the electric current, which depends on the difference between Fermi energies and the transmission function. And when we plot the results following the experimental values, when we plot the current as a function of the gate voltage, we observe that that indeed we have two peaks. And when we plot it as a function of the bias and gate voltage, we observe a diamond structure. Additionally, we observe the same behavior as we explained before. In the maximum of the resonances, we observe a decreasing of the current as a function of temperature, and increasing in the valleys, and a more or less constant value in the middle points. As you can see here, these black curves and these points are the experimental values, and they practically agrees in the same way as the non-interactive model that they explain. So that makes us the question about how to distinguish between the interacting and the non-interacting cases, non-interacting molecules, which, as you can see, they are practically looks the same. So we propose here to apply a magnetic field in order to distinguish between these two cases, which will add to the molecular level a Zeeman term, which depends on the spin. This will have a different behavior in the conductance. For example, for the non-interacting case, its resonance of the conductance will exhibit a splitting of this resonance in two different resonances. On the other hand, for the interacting case, we will observe that its resonance will shift in a direction given by the difference in a spin of the molecule. So we have seen that they have a different behavior its case, and for example, we have shown an experiment that for a ferrocene molecule they apply a magnetic field, and they observe that these two peaks, when they increase the magnetic field, the resonances move. This following what we explained before, we can say that the energy levels, the resonance of this molecule will follow, will be mediated by electron-electron interactions. Okay, let's follow the next the next work, which will be thermoelectric effects in a quantum impurity. Right now we will have a quantum dot, but the quantum dot will be in the quantum limit, and we will apply basically we will hit the left reservoir in order to have a thermal bias. So let me first explain. Let's first find what happens to the Coulomb temperature when we apply a thermal bias. In order to do this, we follow the Coulomb Hamiltonian as we explained before, and we plot the linear electric conductance. Following this, the linear thermoelectric conductance, we will have a regular cotunneling and exchange cotunneling, which right now we have a logarithmic term which will depend on the left and right temperatures. Following this expression, one can define an effective conduct temperature which will depend on the thermal bias of the system. And one can observe that this effective conduct temperature will follow different regimes. For very low temperatures, the conduct temperature stays in the intrinsic conduct temperature and it will stay in the conduct regime. Then, as we increase the thermal bias, the effective conduct temperature will follow a scaling region. And finally, a very large thermal bias, the effective conduct temperature vanishes, yielding the conduct quench, and the conduct effects will be totally vanished. I want to say that this model is valid only for temperatures larger than the conduct temperature. So right now we are going to explain what happens in the other case, and this will we will be accomplished with following the slave boson Hamiltonian for infinite interactions. Right now it will take a similar Hamiltonian than the Anderson model with the Hamiltonian of the leads, but right now we will have a Hamiltonian of the dot with operators F, which creates a state of a given spin in the quantum dot, and a tunnel Hamiltonian, which will also depend on a boson field, which creates a vacuum states in the quantum dot. Finally, in order to have only one electron in the quantum dot, we will give a Lagrangian term which assures this that the quantum dot is only single occupied. I want to stress again that this will be valid only for low temperatures and strong interactions. Following this Hamiltonian, we will go to the slave boson-Millfield theory. That takes the boson operator and takes its expected value, and we will compute two mean field equations: one for the stationary limit of the boson field, and then the Lagrange conditions, that means that only one electron can be in the quantum dot. Following these two equations, one arrives to a complex equation which depends on a non-equilibrium distribution function, which depends on the Fermi function of the leads, and two mean field parameters which will be solved consistently. That for the conduct peak will define the conduct resonance width and the conduct resonance position. Taking the conduct resonance width can be also understood as a effective conduct temperature. So we are going to study what happens when we apply a voltage or a thermal bias. When we apply a voltage, we see that this effective conduct temperature smears as we increase the voltage, and at some point the conduct peak is split into different resonances. On the other hand, for a temperature bias, we observe that that the effective conduct temperature reaches the same point as we explained before. First a conduct regime, then a scaling region, and then the conduct quench, yielding disappearance of the conduct resonance. If we compare both curves, the perturbation expansion and the slave boson-Millfield theory, we observe that both models agree, even though these two models are valid in different regimes of thermal bias. So this makes us sure that to say that the conduct resonance, the conduct effect will disappear when we apply a thermal bias. Okay, following right now I'm going to explain what happens to the transport when to this quantum dot system. When we apply a voltage bias, we observe that that the current will follow a state behavior which is similar to the Hubbard-1 solution, which takes of the Coulomb blockade effect. but with the difference that we have the zero bias anomaly in the conductance, which is a very narrow peak at voltage equals 0. But more interesting is what happens in the temperature bias. What we observe is that we have a very strong nonlinear behavior, and which in some points, for some energies of the quantum dot reaches the quantum dot, the current is reversed, even not one, even 2 times. This can be explained with energy diagrams, and where it takes into account the Fermi functions and the density of states of the quantum dot system. These are three resonances, which is the Kondo resonance, the energy level resonance, and the Coulomb blockade resonance. When we apply a small thermal bias, the window of transport occurs near the Fermi energy. This means that only the Kondo peak plays a role in the transport, and in this case the Kondo peak is shifted slightly above the Fermi energy. This will create a positive current in such a way that the electrons go from the left to the right reservoir. On the other hand, if we increase the thermal bias, this window of transport increases, and then the resonance, which is below the Fermi energy, plays a role, and then the current will be reversed in such a way that electrons go, the net electron also goes in the opposite direction. If we increase more the thermal bias, at the end the Coulomb blockade resonance also plays a role, and the transport will be reversed again. So this is what happens. This is the reason where because we have the thermocurrent presents this nonlinear behavior. Right now we are going to move from one Kondo impurity to double Kondo impurity. In this case, we take a double quantum dot in series, where each quantum dot is connected with only one reservoir, and we will apply a thermal bias. As you can see here, each quantum dot is connected to one reservoir, one would expect that each quantum dot will present a Kondo resonance. But they are connected with each other, so we can expect some kind of competition between the connection between the quantum dots and the connection with the reservoirs, yielding the Kondo effect. This system we will study it using the slave boson Hamiltonian, which in this case the only difference is that right now we have 2 dots, which will be differentiated by gamma, and the dot tunnel amplitude tau. As we explained before, we will go to the slave boson mean field theory, and we will have to the mean field equations of the stationary limit and the single occupied dots. And right now we have 2 renormalized parameters for each quantum dot. And following these gammas can be understood as the effective Kondo temperature will be studied independently its 2 resonances. And we see what is expected for the weak coupling regime, where both dots basically are not lower connected. We see at behavior of 2 independent quantum dots. One of the quantum dots stays more or less constant, and the other quantum dot will decrease the Kondo effect will disappear since the thermal bias will be as a normal temperature. If we go to the intermediate coupling regime, both quantum dots fills each other, but at the end, at very large thermal bias, both quantum dots decouples anyway. For For the strong coupling regime, both at the beginning, both quantum dots feels basically the same behavior, yielding a similar behavior as a single quantum dot. But again, for a very large bias, both quantum dots decouple. This can be seen very clearly in the electric current, where we see three different behaviors in comparison with the regimes. For example, for the weak coupling regime, we see that the current increases and then decreases to zero. For the intermediate coupling regime, what happens is increasing, but then decreases slowly. And for the strong coupling regime, what one finds is that the transmission function will present two different peaks, yielding in different sides of the energy, and we will observe a non-linear behavior, yielding a non-trivial zero. When we observe what happens to the thermal current, we see a strong strong increasing of the thermal heat current, but at some point it reaches a maximum and then decreases. This decreasing, which creates a regime of negative thermal conductance, is due to the coupling of the both quantum dots. Finally, also we have seen that the thermal conductance follows the Fourier's law for each value of the hopping between quantum between dots. This is all for serious this double quantum impurity. Right now, I'm going to explain one of my last works, which is the Coulomb Drag in parallel quantum dots. Well, in this system, what we have is two different subsystems. One will each of them is represented with a quantum dot connected with two reservoirs. These two reservoirs are independent from each other. The difference between these two systems is that in one of them we will apply a voltage bias, and in the other it will stay at equilibrium. Now, nevertheless, these two systems will be connected with the interdot electrostatic energy U. And what happens is when we have asymmetric some asymmetries in this equilibrium system, it will feel the current of the system at non-equilibrium, and will also show electric current. This will be called drag current, and is the thing we are going to study in this work. This system will be also modeled with the Anderson-Hamiltonian, which right now is instead we go to the Coulomb Drag limit, which takes zero interdot coupling. We don't allow hopping between electrons, and infinite intradot interactions in order to only have one electron for each dot. Then anyway, we have the interdot electrostatic energy between quantum dots. Following this, and using the non-equilibrium Green's function formulas, one can obtain this expression of the current, which depends on the self-energies, which has two terms: the interaction self-energy and the tunnel self-energy. But normally we take the interaction self-energy equal to zero. But in this case, we can observe that the drag current will be zero if we don't take into account this interacting self-energy. So this makes us to understand that the interactions are essential for having non-zero drag currents. Then we take the interacting self-energy, which will have two terms. One is the Hartree self-energy, which will shift the resonances with the term with U, and the second term, which is the change correlation energy, which depends on the Green's function of the system and the Green's function of the other subsystem. That can be this can be understood as a polarizability term, and represents the charge fluctuation of the systems, since it follows it depends on this expression. Then, taking these two terms into account, we arrive to this expression of the drag current. And as we can observe here, it will depend on the Green's function of the system, this charge fluctuation of the drive system, the charge fluctuations also of the drag system, and this term, which will depends on the on the hybridization functions of the drag system connected to the leads. This makes us to a condition for not having drag, which is that this connection with this coupling with the reservoirs has to be non-proportional and energy dependent in order to not to have a non-zero drag current. Then this phenomenon will be understood that in the drive system, when we apply a voltage, this will give some energy to the drag system. This what will favor fluctuations in the drag system in such a way that since there exists an asymmetry in the system, a drag current will flow. When we plot the drag and the drive as a function of this drive voltage, we observe that the drag appears when the drive becomes significant, when the drive current becomes significant. Additionally, we observe that the drag depends in a parabolic behavior at low voltages, but this is not does not occur always when because we have assumed proportional drive couplings. If we assume non-proportional drive couplings, what we will obtain is also a linear behavior of the drag current. Finally, when we plot this drag as a function of the level of the quantum dots, we observe that the transport will only occur around the triple points, meaning that one makes that the drag will be important only when when cotunnel processes appears. Now we go to a strong interaction regime, which this is the last part, which is not in the thesis, but it was studied at the last point. This will go to the orbital Conde effect, where right now, instead of having the spins, we have the quantum dots. We will play as a pseudo spin, and they will present also a Kondo resonance. One characteristic of what we have found of this strong interaction regime is that when we plot this drag as a function of the voltage, the drag current is diminished when the Kondo effect, when there are Kondo correlations. Additionally, when we plot the second order transconductance, we observe some kind of zero bias anomaly of the drag current. And finally, we can observe that when we plot as a function of this charging energy, the drag current has an optimal value, which corresponds when the interaction energy is of the order of the amplitude of the coupling. Additionally, this this drag current has been also modeled with taking the quaternion effects of the Kondo-Hamiltonian, which takes this expression of the drag current. And we have observed that at large interactions agrees with the Green's function model of before, which makes us sure of the validity of both models. So these were all the words I wanted to explain here. Let me go to the conclusions right now. The main goals of this thesis was took interactions in the quantum dot systems, and we have focused on the study of nonlinear quantum transport when we apply voltage and thermal biases. Additionally, we wanted to characterize what happens to the Kondo correlations when we apply a thermal gradient in the system. In the first work, we have studied molecular junctions, and we have shown that a Coulomb blocking model can fit the experimental the temperature dependence of an experiment. And we have proposed, in order to distinguish between non-interacting molecules and interacting molecules, to apply a magnetic field which will induce a Zeeman splitting when the molecules are non-interacting, and a level shift of the resonance of the conductance when these molecules are interacting. For the next work, we have studied the Kondo effect of a quantum dot, and we have observed a splitting of the Kondo resonance when we apply a voltage, and a smithing and disappearance at large thermal biases. We have used several models, and we have made to the conclusion that the Kondo peak is destroyed when at very large thermal biases. And additionally, we have observed additional zeros in zeros of non-trivial zeros of the thermocurrent, also induced by the Kondo effect. For the next work, we have studied two impurity Kondo system, and we have observed three different regions depending on the coupling between the quantum dots as in comparison with the coupling with the leads. We have observed that these regions can be observed with the thermoelectric transport, which in the strong coupling regime leads to non-trivial zeros, and in the thermal transport we have observed a strong nonlinear behavior. The last work, we have studied the Coulomb Drag, and we have shown that we need energy-dependent dot-lead couplings in order to have drag. Also, we have shown that drag is driven by charge fluctuations with this polarizability term of the drag current. And in the orbital Kondo regime, we have observed that Kondo correlation destroys the drag, and using a Kondo model, we have observed an agreement with the model we have applied. These were all works. Let me explain what possible future work in order to study. One thing one can do is to study the techniques with different techniques, the models I explained before. For example, the numerical renormalization group, which is valid for all temperatures, but the non-equilibrium effects are difficult to study in this system. Also, we can take the slave boson but without the mean field approach, or to include the mean non-infinite Coulomb interactions in order to see the mean particle peaks. Additionally, we can study different other parameters in the systems of this thesis. For example, we can study spin currents, or we can study the, systems with different couplings. Of course, in the last work of this thesis, I have studied this situation, but in the others I have not. So it will be an interesting interesting thing to study. Additionally, the thermoelectric drag, one can study the thermoelectric drag when instead of having a voltage bias in this drive system, we have a thermal bias in this drag system. Finally, another change that one can study is the different configurations. Well, for example, instead of double quantum dot that we have explained in series, and in parallel we have studied in the main manuscript, one work, one can study triple quantum dots, where here one can observe interference effects. Additionally, one can go to more quantum dots and having quantum dot arrays or quantum dot chains. And another different configuration can be to have different type of leads in order to which will have different energy dependencies of the couplings between the quantum dots. With all of this, I have finished with my presentation, and right now I will be pleased to answer your questions.
Thank you, Miguel, for a very nice presentation. And now we should go to the questions, but I understand that it's possible for those who do not wish to listen to the question that they can leave the room. Let's give them a very short chance.